Hi, good everyone. Welcome back to this channel. My name is Godwin, as you probably already know. And if you're meeting me for the first time on this YouTube channel, so thank you for joining us. We hope you have a very good time. So we'll be looking at starting something kind of a little bit new today. Um, Looking at statistics because the essence of this particular series is to get into econometrics to make us understand econometrics better. Okay, but then we need to just look at the foundation of some of the things that will be needed that we are going to be needing in econometrics. So today we're looking at normal distribution. All right. So now the thing is that basically in life, by the time you look at any particular variable, let's say wealth, income of people, right? Let's say, I don't know, let's say achievements and all of those things. Okay, let's even talk about people's height. Okay, I don't know if you've probably observed that we kind of have a kind of distribution. Okay, when we say distribution, like looking at everybody together, we kind of have some people that are, you know, okay, let's look at height, for example. Some people are very short, do you understand? And then some people are very tall. But then the majority of humanity lies within an average height. Do you understand? Like we are not the majority of us are not that really taller than each other. But then we have some people that are like giants, so tall they are rare to find, but they are possible to find, right? And then you have people that are very short, apologies to the short people, here. All right, and then when you look at them too, like they are still not as many as the bulk of humanity that is of an average height. Now, the same thing when we look at income, for example, you look at a given profession, any given profession, you have people that are seriously not making it in that profession, they are really, really struggling. You have them at the bottom. Then you have people that are you have like maybe like the top 5%, people that are the greatest achievers in that particular field of profession or in that particular field or profession. So you have them, extremely, the extremely brilliant, set of people, the extremely brilliant, the extremely successful people or wealthy people and thereabout. You have them, not as many as well. And by you find the rest of the world like, in the center. People that end up calling maybe lower middle class, upper middle class, like you find the bulk of humanity around that, region. Now, the same thing if you look at test scores of students, basically speaking, you have those that are going to, let's say, let me even say examination scores, and you have 100 over 100. That's like the total score. You may have like one or two students, let's say in a class of 20, you may have like one or two students having like 99, 100, 98, let's say three students. And then you may have like three students failing, you understand, maybe like 30, 41, 45. And then the rest of the class just falls within the center. All right. So when we have things like that, we are saying that okay, when we look at the bulk of the distribution of different variables in the world. Now, most of them are normally distributed. So now what does normal distribution mean? What does normal distribution mean? So we have a normal distribution, right, which is what we have. A variable has a normal distribution if its distribution has the shape of a normal curve. All right, a normal curve or a bell curve. Now, a normal curve, this is a normal curve here. It looks like a bell. Do you understand? It has a tail. So this is a tail here. This is a tail here. Then you have the bulk of the distribution. When looking at distribution is about it's like data. For example, like the exam scores I spoke about, people having different scores, 20 different scores. So what we are saying is that we'll likely find about maybe like two of the scores here, and then find like two of the scores here. Then 16 of them are now going to be like in the center here. So that's what we're trying to say. All right. So when we have things like that, we say that okay, this variable has a normal distribution. So that's how it works. This variable has a normal distribution. Okay, I've already mentioned that a normal curve is the same thing as a bell curve. So if you have a variable that has a distribution, all right, that has the shape of a bell curve, now it is the variable is normally distributed. Okay, so that's about that. What else are we supposed to know? Now, all variables are not exactly like this, but then they are kind of approximately normally distributed. Like they are very, very close to being normally distributed. And then we have others that are not, normally distributed at all, right? So they could be skewed to the right. All right. So when we say it is a variable is skewed to the right, that's a positive skew. We are talking about is this my green marker? So we are talking about this. Okay, of course, this is not a normal distribution. Okay, we are talking about, so this has a positive skew. Okay, so this is a positively skewed distribution. All right, and then we have the other way around, which is the negatively skewed distribution. I don't really have a space to do that. So let me just kind of do it here. Negatively skewed is skewed towards the left. So you have something like this. Yeah, something like this. Now, basically speaking, this negative a negatively skewed distribution, a negative when you have like um the distribution is not like you don't have okay. Mm, all right. Let me look at it this way. For a normal distribution, the center is the median, right? The center is the median. So here, I was supposed to talk about that looking at this, but then it's okay. The center is the median. So here, this is the median. All right. So when you have a distribution, okay, that's when you have when you have a normal curve that shows that distribution are equally distributed on either side of the center. So that's another way to also like explain a normal distribution. Now this is the center, right? So we say that this distribution is uh, is symmetrically, we say that this variable is symmetrically distributed around the center. Symmetrically distributed means that it has a line that divides the distribution into equal halves. Okay, now this line that divides the distribution into equal halves. Now let me look at, now this is my what do you call it? This is a lesson note. Like, do you understand? So like if I divide this into half, if I divide this into half, like a demonstration, if I divide this into half, is it exactly half? Okay, so this line, I've done that. Now, this line here is a line of symmetry. Okay, a line that divides this paper into equal halves, into equal parts. Do you understand? So, which exactly what is happening here? You have a line at the center, you know, dividing the distribution into equal halves. Right. So this part is this part, the area here is as equal, is equal to the area here. So that is exactly what we have there. Now by the time you okay now before even moving there, for a normal distribution, this center, which is the median, is same as the mean. So the median is same as the median is equal to the mean, and it is also equal to the mode. All right. So of course, what we have here is probability of percentages. So what you have on this axis is probability of percentages. Um, then like a graph, something like this. Okay, so this is telling you that you have a high percentage or high probability of having this value. Okay, whatever value is here, which I call the center, which but officially like I call it the mean. This is all right. So this distribution, there's a high percentage of getting this value, okay, or there's a higher chance of getting this value. And then we've spoken about probability. Okay, we did stuff on probability. So now this is essentially trying to tell us that okay, why is it that you're going to have more chance of this mean value? Isn't it because the mean value is occurring the most, okay, of all of the distributions? Do you understand? And that's is telling that it is the mode, the same as the mode. Now, this is not always the case if you have more than one mode. For example, if you have a bimodal, form of data set, so you have more than one mode. But when you have just one mode, like the median, the mean, and the median and the mode of a normal distribution, they are equal. Are you getting it? Now, by the time we begin to look at possibly skewed, so the thing is that this is the median. This is the median, right? This is the median. Um, and then after this is the mode, right? This is the mode. This is the mode. Sorry, this is the mode. Then the median follows. The median follows. You have median, and then you have the mean. You have the mean. All right. So of course, this is like the highest. Whatever you have here is telling that okay, it has highest chance of happening. Of course, That means it occurs like more often than the other ones. Then after the mode, you have your median, the one that divides the whole thing into two, and then you have your mean. So you see that it is not the same. All right. So this is trying to tell you that you have more of a distribution on one side than on the other side. Okay, which is not supposed to be the case if you're looking at a normal distribution. Now, same thing for this. You have more of a distribution on the other side. Like there's no line of there's or the this line, right, is not can we call this a line of symmetry here? This is asymmetrically distributed. So this is not a line of symmetry because you have more to one side, more of the distribution of the variable to one side. For example, scores of students, more of the scores of the students to one side than on the other side. Okay, so that's that about that. Then this one, of course, the height here is still the mode. Then the median, then the mean. All right. So for a negatively skewed distribution, you also have what do you call it now? You also have it's also asymmetrically distributed. Asymmetrically distributed. So now, that's being that. I think let's begin to move into properties of a normal distribution. It is determined by the mean and the standard deviation. Okay. Now the mean. Right, I said for a normal distribution because we're fortunate that the mean is same as the median, so we can just the mean is the center. As do you understand? So like we just use the mean. All right, so it is determined by the mean and standard deviation. So the mean determines the height of your normal curve, okay, and then the standard deviation determines the width. Standard deviation is talking about the spread, okay, of your normal curve. Now look at the mean here, because the mean is still same as the mode anyway. So look at how high it is. Now we can have another one. I can just superimpose. Um, I think let me clean this so that we don't begin to have too many things. So looking at these distributions, both of them are normal distributions because they are symmetrically the distribution of the variables that we are looking at. For the first one is baby height, and then for the other one is adult height. They are symmetrically distributed, okay, around the mean. Okay, and I think one thing I should correct from the other stuff I drew the other time was we have a population mean, not the by x. The by x is the sample mean. So population mean is written as mu, then the sample mean is written as the by x and what have you. So now, if you look at this is telling us that the average height of a child is 20 inches. So let's say that height is being measured in inches. So the average height of a child is 20 inches. All right. And then there's a 40% probability. Okay, 0.4, when you combine to percentage, there's a 40% probability that every a particular child has an height of 20 inches. Right. Then if you look at this other one talking about adult height, and yeah, so mean. Then standard deviation is looking at how spread out the distribution is. So if you look at this particular distribution, so which one is more spread out? Is it the adult height or the baby height? Of course, the adult height. Do you understand? So here, this is essentially telling us that there is a 17% probability that an adult is, um, 17 inches in height. Do you understand? But then the probability of that, okay, okay, I've just said that together. Okay, the mean is 17 inches, then 17%, probability. So the percentage is, lesser than, what we have in this particular place. And then if you look at how spread out the distribution is, this is more spread out than this particular distribution. So we expect that this is not even that we expect. What is happening that the standard deviation here is more than standard deviation here, okay, because standard deviation is a measure of spread. Okay, is a measure of spread. So if, for example, the standard deviation here I was like to be let me say 4. So the standard deviation here is maybe standard deviation here is maybe 7. Okay, 7. All right, so standard deviation just tells you how spread out, a distribution is. All right, that's being said, I think we've explained point one. It is determined by the mean and the standard deviation. We are still going to, in our next class, we are going to be converting this to a standard normal curve, right? Which is kind of easier to work with because we'll be looking at this cause and thereabout. Now, it is determined by the mean and the standard deviation. If the distribution is symmetrically distributed about the mean value on both sides, okay, we say that x is normally distributed. I've explained that. Then the second one says that the spread of a normal distribution is determined by the standard deviation. So, which I just explained, the spread of a normal distribution is determined by the standard deviation. The more the standard deviation, that is, the more spread out, you know, a particular distribution is, for example, test of students, the more spread out it is around the mean, the flatter is the normal curve. Okay, the flatter is the normal curve. So if you were standing like this, for example, and then maybe doing an exercise and then you have to stretch, to stretch, to stretch your legs, stretch, you'll be going down. You see that your height begins to reduce. All right, and then by the time you're bringing it together back, you see that your height, increases. You stretch again, you begin to like. Do you understand? So that's what is happening here. So this thing is like the distribution is like stretching its legs. So the more it stretches, the lower the height is going to be. So that's what we mean by flatter. And the more it comes closer together, the higher the height is going to be. Okay. All right. The third feature: two normally distributed variables having the same mean. They happen to have the same mean. They happen to have the same standard deviation. Then obviously they are like the same. So like two normally distributed variables, variable x and variable y, for example, having the same value of the mean, they have the same standard deviation, then they must have the same distribution. As I guess that is supposed to be self-explanatory because they're like essentially the same thing. So if two of the important features are already like in tandem, standard deviation is the same, mean is the same, then they must have the same distribution. So now number four, for a normally distributed variable, approximately 95% of all of its observations lie within two standard deviations of the mean value on either side. Two standard deviation of the mean value on either side. So now you may begin to like wonder, like, okay. So what does that mean? How do we explain that? So here, remember that what we have here is the mean value. So when we say two standard deviation. Standard deviation is just talking about how spread out a particular observation is from the mean value here from the population mean. So how spread out, that's if we're able to be dealing with the entire data set. Okay, so how spread out is a particular observation away, from the mean value. So now that's the deviation. So now we are now saying that at best, okay, for you to know if a distribution is normally if a distribution is normally distributed. So one thing I should note is that okay, as like the worst thing that can happen. So I think the worst thing that can happen is that a particular observation is within two standard deviation away from the mean value, either to the right or to the left, and then that is true for about 95% of all of the observations. So anyone that's so you have like 5%, there's a freedom of 5% being far away away from the 95% that is inside of your you know now let me just show you what that is trying to talk about. So what we are saying essentially is that here is my so what we are saying essentially is that most of let me okay, this is not how do we get the mean of I think I should have even erased this one. So baby height, I think we had this. Okay, let me just withdraw it and so a smaller standard deviation. I think we had a standard deviation of 4, for example, and then the mean here was 20. Uh, okay. So what we are trying to say is that for a normal distribution, so one standard deviation away from 20 is 20 plus one standard deviation, so which is 20 plus 1 into bracket 4, and that gives us 24. So we have like I think let me spread this guy out a little um bit more. So I think let's say we have something like this. Oh no, this is worse. Okay, let's just manage this. So we are trying to say, let's just manage that. Trying to say that if the mean value is 20, so we have first standard deviation is 24, and then two standard deviation away. That's going to be 20 plus 2r, which is 20 plus 2 into bracket 4, which is 28. So we're talking about the height of the kids. So like here is going to be 28. So that's on one side, on the right hand side of the mean. Now I do the same thing for the left hand side of the mean. So we have 20 minus 1 standard deviation, 20 minus 1 into bracket 4, that's 16. Yeah. So and then 20 minus 2 standard deviations, 20 minus 2 into bracket 4, and that is 12. So here we have 16, and just here we have 12. So we're talking about, so we are saying that here contains, that's saying that here contains 95% of the entire observation. So it's standard. Okay, it's a standard principle, 95% of the entire observation. So on the, since this is a symmetrical distribution, all right, so what we only have left for this place is a 2.5%. Like we may have the height of a baby that falls, 2.5, like that falls towards this side, like it's kind of outside, like extreme. Then you have 2.5% here as well. So like you may have the height of a child that's like 30, so 30 falls, more than two standard deviation away from the mean. And then here you may have a baby's height of like, let's say 10 or 5, so it falls within, you know it falls outside of, two standard deviation away from the mean. I don't know if what I said just made any sense. Okay, so like this is standard. So we are going to be needing this in subsequent classes. So like just understand it. For a normally distributed variable, 95% of its observation lie within, you know, two standard deviation like distance away from, the mean value of that particular distribution towards the right and towards the left. Do you understand? So whatever height we are going to get, we are 95% like confident that it's within, two standard deviations away from. So that's what that point is trying to explain over there. Like I said, we'll be needing this in subsequent classes. Like just get, it's not difficult. It's not difficult. Now there, I think what I should like talk about next is, although it's not here, there in case you are doing analysis, in case you are running data analysis and then you want to know if your data is normally distributed, so you punch in your numbers into a particular statistical software. So you can use histogram to know, right? And then there's something that's called normality plots. You guys a normality plot to also know if a variable is, you know, normally distributed. Okay. So we want to try to identify normality using histograms and normality plots. Now using histograms, you have two histograms here, histogram A and B, and then we have two normality plots here. So you have a normal scores on that axis, and then um, the scores of the variables on this side. So your normality plot starts from like minus 3, and then to 3. So now how do we use our histogram to know if a variable is normally distributed? So what we just have to do is to draw a line, okay, like a density plot to show the shape of this distribution. So we draw a line touching the edges here. So if you look at this, it is approximately um showing a normal distribution. Okay, like it's like an approximate, like a random scale, it's an approximate normally distributed variable. Then when we try to look at this one, we have okay. So this one is showing something like this. This other guy is showing something like this. All right. So I don't know if if you really if you get the gist of what I'm trying to tell you. All right. So the first one is showing okay this variable is normally distributed. It's approximately normally distributed, and then this variable is positively skewed. Okay, revise positively skewed. So as an assignment, what I just have to do is to draw a histogram that shows a negatively skewed variable. That's all. Draw a histogram that shows a negatively skewed variable. So here, this what we have down here. These are normality plots. So you have the normal scores on this axis. Normal scores like you have -3 to 3. Okay. So now when we look at the line, so how do they cluster? Are they kind of trying to show you that you have a linear curve? Okay, are they trying to show that you have a linear curve, or they are trying to show you that you have a non-linear curve? So the thing is that for you to know if it is normally distributed using your normality um, plot, so your observations, right, must be clustered along a linear curve. So they must show that there is a kind of linearity. So I can just, if I draw this, I can draw this like this. So you have this is a linear line. So you have this like approximately what do you call it now? Normally distributed. But if we try to do the same thing here, we have something like this. Like our okay, let me use this. So we have something like this. So this is not linear. This is not what do you call it? This is not normal. So whatever you have that is not giving you a sign of a linear curve is telling that your variable is not normally distributed with the use of normality plot. Okay, then what if under a normality plot you have something like this? Let me say you have something like this here. So there's an observation here. Now, most of your observations are along, they are clustered around a linear curve. Most of your observations are clustered along a linear. Whether you now have one particular observation somewhere else. So this is called an outlier. Okay, an outlier is an observation or a figure that has, a drastically different value than the majority of, or than the rest of the, values of the observations, okay, or something like that. So here, for example, you have in the test score, so you have somebody, most people got 50 something, 60 something, 40 no 50 something, 60 something, and then somebody goes on to get like 2. Okay, when the majority of the class is scoring like 50% and above, somebody goes on to get like 2. You understand? Like, wow, that's so drastic. So in an analysis, you try to like eliminate the impact of the outlier, like you remove this guy. Some of the reasons that may warrant an outlier, number one, there might be mistake while computation is being done. Do you understand? There might be mistake. For example, let's look at maybe height. Let's look at like maybe like heights of people. We want to measure heights of people in like meters, and then the re- the rest of the data set is measured in meters, and then you mistakenly um, represented the other one in centimeters. This one is centimeters. Of course, it's going to be like drastically different from the rest, of the figures that you have in your normality plot. And then it might be also due to like other kind of mistakes, and then it might be due to like a different. I don't know. For example, in Nigeria, let's say you are trying to look at the GDP per capita. You are trying to like show normality plot for GDP per capita. Now, the bulk of Nigeria's population is poor, like multidimensionally poor. But then if you go and include somewhere like Dangote in your data sets, you understand of your variable, because Dangote earns so much, do you understand? His impact is going to like bloat what you're trying to do. It's going to like bloat your analysis. It's going to give you a wrong figure of what your average analysis is, because you're trying to look at the life of an average Nigerian person. Okay, the life of your average Nigerian person, and then you go and bring in one multi-billionaire and then add him to, so it makes the loss look like they are so rich. Do you understand? Whereas it's only one person or like two people that are that excessively wealthy in the country. So you just have to like eliminate their impact, just remove it, and then focus on the rest of the data set. So if after removing the outlier, the rest of the data set should still show something like a linearity, still show a linearity, then you have what do you call it now? You have a normal. Alright, that's essentially a wrap for today's video. For this particular class. Alright, so as an assignment, like I mentioned earlier, just sketch out a histogram that shows a negatively skewed distribution, and then find out like three other reasons why there might be an outlier in a particular distribution. Find out three other reasons why there might be an outlier in a particular distribution with examples. Then why should an outlier be eliminated from, a distribution? Okay, why should an outlier be eliminated from it? There's two reasons why an outlier should be eliminated from the distribution. So that's it. Thank you very much for this video. See you in the next one.